We're picking up where we left off yesterday. So this is the tail end of section 4. You have a function here, right? Do you see how, like, if you wanted to trace this function, it goes up and then it goes down, right? So if we wanted to look at this interval from x1 to x2, okay? And if you look at the y value of this function over the interval x1 to x2, so at x1, this is the y value, and then it increases and increases, and then it decreases, decreases, decreases. So the y value is definitely changing as we go from x1 to x2. Now, the question is it changing quickly? Is it changing slowly? More specifically, how fast is it changing? What is the rate of change on average? Average rate of change. To do that, okay, if I want to find the average rate of change between 2 points, what I do is I mark those 2 points and I draw a line that crosses those 2 points. When the line crosses those 2 points, when it passes through those 2 points, it passes through the function twice. And if you remember from geometry, a line that passes through a circle twice was called a secant line, versus a tangent line which hits a circle how many times? Once. Okay? So I draw a line and it's that secant. Now, if I were to find the slope of that line, okay, that would tell me how the value of that function is changing on average. Okay? In other words, that would be the average rate of change. Right? So to find the average rate of change, you draw a line between them and then you find the slope. Okay? So, in practicality, it is a very straightforward application. Okay? So, if you wanted to find the average rate of change for the function here on this interval, what you would be looking for then is the slope m of the secant line, and that's f of -1 minus f of -3. Why -3 to 1? Because it's this. This is x1, this is x2. Okay? Over -1 minus -3. So f of -1, if we plug a -1 into that function, how much is it? -2 minus 4 plus 6, is that 0? Minus f of -3, so it's -2 times 9, -18, minus 12, plus 6, how much is that? Is it -24? -24. So it's positive 24 over 2. So that's 12. Whose phone is that?
Always mine.
Huh?
Turn it off.
Ooh. There's an idea. If only I had mentioned that before. Okay. So take a look at this one. Okay. I've given you the points. So now you have to figure out this is x equals 2. This is x equals 4. Right? So the slope of the secant line is going to be f of 4 minus f of 2 over 4 minus 2. Okay, f of 4, you just have to look now. It's how much? -2 minus, how much is that? 2 over, oh yeah. So that's -4 over 2, -2. Okay?
Wait, would you plug in? Would you plug in like f of negative, f of 4?
I'm not plugging anything in. I'm just looking at the value of the function here on the graph. At x equals 4, y is negative 2. Okay?
Can't you just count the slope?
You can if this was Algebra 1, but in Precalc Honors, we do it in a more elegant, sophisticated way. Okay? If you want to get invited to any of those math parties. Okay? So now you could finish that one, the homework for this one. We're going to do problems tomorrow. Okay? We have an extended period. Okay, now,
When's the next like 10 more please there?
we'll talk about that later. We're moving on to section 5.
Aren't these negative? How's it positive?
Well, we got 0 minus negative 24.
Oh.
Okay. All right. We're talking about parent functions. One of the objectives of pre-calculus is for you to be able to graph practically every single type of function manually without a calculator. All right? So we're going to start slow by going over functions that you've seen before and you've already graphed before in previous years. So a family of functions, right, is basically a group of functions that have the same characteristics. Like, for example, how many different equations can you come up with that graph a parabola? An infinite number. Those are all a family of functions. How many different equations can you come up with that graph a line? Oh my gosh, an infinite amount. Okay? Those are all a family of functions. These families of functions, just like families of humans, have parents. There is a parent function. In the case of the parabola, the parent function is x squared. In the case of the line, the parent function is y equals x. And everything else, okay, like this one, for example, the parent function is x squared, and everything else is an embellishment from that, of that, okay? All right, so let's talk about some of our functions. At first, I have a constant function. A constant function is when you have y equals a number, y equals a, y equals c. A more concrete example, y equals 5, y equals negative 3. Basically, you just get a horizontal line. Okay? All right. Next is the identity function. By the way, it doesn't have to be y equals 5. The better way to write it is f of x equals 5. The identity function, we're used to seeing it as y equals x. It's f of x is equal to x. Why is it the identity function? Because when x equals 5, what's y? 5. When x equals negative 2, what's y? When x equals 3, what's y? Do you see how it's the identity? Right, you just get the same thing back. So that's an identity function, okay? The coordinates are always a. All right, next is the quadratic function, f of x equals x squared. We know all this. Cubic function is x cubed, okay? X cubed looks like this. Let's think about this for a minute, okay? When for positive x's, is f of x positive or negative? Positive. So when the x values are positive, f of x is positive, meaning it's above the x-axis. For negative x's, what's f of x? Positive or negative? Negative. Negative meaning it's below the x-axis. When x is 0, what's f of 0? 0. Okay? So think about that. It's always increasing. Next, the square root function. The square root function looks like this. So what do we know about domain for the square root function?
Greater than 0.
X, the stuff inside must always be greater than 0. So it's greater than or equal to 0. So it's defined from 0 to infinity. Okay? So for example, can x be a negative number?
No.
No. Can it be 0? Yes. Okay. Next is the reciprocal function, one of my favorites. Okay? The reciprocal function is defined as 1 over x. So let's just talk about that for a minute. Let's talk about domain for a minute. Okay? Can x be negative?
Yeah.
Yeah. Can x be positive?
Yeah.
Yeah. Can x be 0? No. So domain is negative infinity to 0, 0 to infinity. So x can never be 0. Okay? What about y? Can you plug in a value here to get a positive value for y? Can you plug in any numbers for x to get a positive value for y? Yeah, like you could plug in 2 and you get positive 1/2. You could plug in 10 and you get positive 1/10, right? Can you plug in numbers for x to get a negative value? Can you plug in a value for x to get y equals 0? Is there any number that you could put in the denominator there that would make this entire thing 0? No. So not only can x never be 0, neither can y. Okay? X can never be 0, y can never be 0. What does that mean? Asymptote here, precisely, and asymptote there. Okay? So x can never be 0, which means there is a horizontal asymptote.
So would range be the same as
Yeah. And y can never be 0, so there is a vertical asymptote. Okay. Let's move on. Absolute value. Is there a value? So absolute value looks like this. Is there a value for that? Is there an x value that will never work in this equation?
No.
No. Any x value will work in this. Is there an x value that would give you a negative y value?
No. But
No.
it's a negative.
Right. So you can put in any x value that you want, but the function will never be negative. It will never go below the x-axis. Okay? And absolute value looks like this. So for example, if x equals 1, you get 1. If x equals negative 1, you still get 1. If x equals 5, you get 5. If x equals negative 5, you still get 5. Okay? Okay. Next. Okay, so I lied. This is my favorite function. This is the greatest integer function, and it pains me that it's sort of like little by little it's disappearing out of the math world. But man, I love this function. This is like every time you send an electronic pulse, let's say like a pulse wave, that's an integer function. What it is the y values can only be integers. So for example, for the absolute value, can you plug in an x so that you get y equals 1.7? Sure. Can you plug in an x so that you get y equals 2.2? Sure. Here, not the case. No matter what x you plug in, the y values are only integers. Y can only be 1, 2, 3, negative 5, negative 7, negative 2. So take a look at what this looks like. For the entire time that x is between 0 and 1, y is 1. For the entire time that x is between 1 and 2, y is 1. Okay, so it's called a step function for obvious reasons, and the greatest integer function. I'm just putting it there so you guys know that it exists. I do. That's where I was last year. Those are the best. And we talk about these things like, should students be rationalizing the denominator? Those things come up. Okay? Should we be teaching section 5.2, which we skipped? Those things come up. Okay? Okay. So these are the parent functions. Now, obviously, not every absolute value graph looks like that. Centered at the origin, nice and neat. No. Slope of 1. No. Not every square root, not every parabola looks like that, right? So those other embellishments, like I said before, in mathematical terms, are called transformations of the graph. Okay? So a transformation of a parent function can change the appearance of the parent function. All right. Let's talk about a translation. A translation basically shifts the graph up or down. Okay? So let's talk about a vertical translation. Okay? A vertical translation is one that moves the graph vertically, either up or down. So basically, you take f of x and you add a value k to it. So for example, suppose here this blue function, f of x, was x squared. The green function would be f of x equal to x squared plus 4. Okay, that moves it up. And then x squared minus 4, that moves it down. All right? Okay, horizontal. This is all stuff that you guys know. Okay, horizontal. If this is f of x equals x squared, this green one would be g of x equal to x. Okay, let's say you moved it to the right 3 units. What would it be? Minus or plus? Minus 3 squared. Okay? And if you moved it to the left, it would be, yeah. All right? So, let's use this on x cubed. Okay, what does the first one do? Move it down 3. So the center is going to be here. Okay, now if you just looked at x cubed, okay, let's take a look here at x cubed. If you started from the center, if you go over 1, how much do you go up? How much do you go up? 1. If you go over 2, how much do you go up? 8. 2 cubed, right? So here, if you go over 1, you go up 1 or down 1. And then if you go over 2, you go up 8. So that would be like up to 5 here. Okay? At least get like the middle 3 points right. Okay, the next one. Where do we move it? Up 2 and to the right 4. And again, up 1 over 1, down 1 over 1. And then it's going to go, if you went 2 up, it's going to go 8 up, right? So you're not going to go too far out. Okay? There is some eyeballing, but at least get those middle 3. Okay.
You wouldn't have to plug it in and then find the y by solving out.
No.
You do 2 minus 4 squared.
No. Just know that if you go over 1, you go up 1. If you go over 2, you go up the cube of 2. Yeah. Okay. Reflections. A graph is reflected around the x-axis if you have a negative out front. Okay? Now, if x is negative, the graph is reflected along the y-axis. Okay? So, take a look at these two. Thank you. So take a look at these two. You have negative root x plus 4. Now, what does root x look like? Let's just graph root x here. Thank you. What does root x look like? Here, if I go over 1, I go up 1. And then how much would I go across in order to go up 2 units?
4.
It's 4. I would have to go 4 over to go up 2. I would have to go 9 over to go up 3. Do you guys remember this? Right? Those of you, especially like in Algebra 2 Honors, I really tried to like stress this last year. Okay, so now we're going to do the same thing, except what transformations have happened here? It went up 4, and this is a reflection. Right? So we're going to start here. And now there is a reflection around the x-axis. That means, it's okay, Emma, you can leave it there. Yeah. That means if I go over 1, I go down 1. If I go over 4, I go down 2. Yes? If I go over 9, I go down 3. Okay? So that's what it would look like. You don't really have to show me the one in the black. I just did it for us to get practice on how to do the points. What about the next one? Where does it go? Starts at where? -1 and up 2, right? Here. B. No, that's it. We're done. We're done with A. So the next one, we're going to go over 1, down 1. Over 4, down 2. And then over 9, down 3.
Since it starts at -1, wouldn't it be at 3 0?
Oh, yeah. Oh, yeah. Sorry. So here and here. Okay. So you see that? No calculator needed. All right? And look at what a nice, precise little graph we have there.
What would it look like if it flipped?
Horizontally?
Reflection on the y-axis?
Like this.
I mean, like in the,
Yeah.
like the equation.
Oh, the equation. It would be with a negative in here.
Oh, and now.
Yeah. If you go down, instead of going to the right, you would go to the left one. So you start from here, down to the right, down, you go to the right one, down 1. And then you go to the right 4 and down 2. You see what I mean? Okay? All right. Next. All right, so vertical and horizontal dilations. A vertical dilation is when basically like you stretch it vertically. So you have a factor in front, right? So for example, if y is equal to x squared, then the new function would be, g of x is equal to 2x squared. That means when you're graphing a parabola, if you go to the right 2, how much would you go up? If it's just y equals x squared? 4. But if it's 2x squared, then you go twice that. So instead of going up 4, you go up faster. Okay? So for each increment that you go over, you have to go up twice. That's what it would mean. Horizontal dilation is if you have, for example, g of x is equal to 3x squared, like this. Okay? So basically, you know how for y equals x squared, you would have to go over 2 in order to go up 4? If there was a horizontal dilation, you would go up 1 and go up 4. Right? So you go up more and more quickly. Okay? All right, so take a look at this. What is this going to look like? Absolute value that faces which way? Down. So this is going to go, so it's negative 4x, right? So we're going to start here. Now, normally if I went over 1, I would go down 1, right? This time we're going to go down 4 because it's like, you have to move over 4 times as little in order to go down 1. So this one you're going to go down 4 and down 4. Okay? Yeah. Okay. And I did just graph the first 3 points and then I eyeballed the rest. Okay, take a look at this. 1 over 4x squared. All right. So x squared, it's a parabola, starts here. Now, normally, if I went over 1, I would go up 1, but now I have to go 1/4 of that here. If I went over 2, I would go up 4, but now I'm going to go 1/4 of that here. Okay, so it's going to be a much wider parabola. All right?
So yeah, 2 would be 1.
Yeah, it would be 1.
Wait, how?
If we went over 2, we would have to go up 4 normally. But now we're going 1/4 of 4, which is 1. 1/4. If you went over 1, then it's 1/4. If you went over 1, you would have to go up 1 squared, which is 1.
Divided by 4.
But now it's 1/4.
But then, like, for 2, it's 2 squared, which is 4, and then divide that by 4. Oh, that's 1. Okay.
It's okay. Okay, so let's graph these. Let's graph these. X equals 0. Hey, I have a partition. Okay. And then I have another one at x equals 3. So now I'm going to graph these. You know what? I'm not going to do the helpful line this time. So at x equals 0, these two functions meet. Okay? Okay, at x is 0, how much is the value of the top function? 3. Open or closed? Open. And now the slope there is negative 1. So it looks like this. Is that right? Okay, the next function goes from 0 to 3. At 0, what's the value of that function? That's negative x going down.
Oh, negative.
So it's 0 and it's closed. And then what other point do I plug into that one? 3, and it's how much there? 6. And now it's an open circle. And really, like, there is one way to graph this because it's a line. I just connect those 2 points, right? Can't get more boring than that. Hey, what happened? Why can't I write this? Oh, I see. Okay. Now I have a root function. Okay, what do I plug in? 3. And what do I get for that value? Root 4, which is 2, and it's a closed circle?
Yeah.
Yeah? And then what else?
8 would equal 3.
8 would equal 3. Good.
That's what you call smooth.
Huh?
It's 8 plus 1.
So he just plugged in a function, a number that would give you a perfect root, a perfect square.
You want us to put like arrows at the
No. Okay, cool. Don't you love piecewise functions now? Right? Come on, they're so cool. All right, so take a look at this, absolute values. So x plus 2, right? Where is the vertex for this one? Where?
no minus.
Negative 2, right?
Yeah.
So, that's an absolute value function, right? And the vertex, so this has moved to the right, to the left too. So really, it looks like this. Okay? So look, I just did that without plugging anything in. Did I do it correctly at x equals 0? Does it have a value of 2?
Yeah.
It does, and it's an open circle there.
Wait, so I'm confused. So like for the square root function, you don't do the vertical or horizontal. You don't do the horizontal shift inside.
No, because the thing is, that's x plus 1. All that says is, had I stretched this further, it would have met, like it would have, the end point would have been at x equals negative 1. But I'm not going to graph any of that because it doesn't fall into my domain, right? It doesn't fall into the range, the interval. So basically for the piecewise functions, you just sort of like have to take it as you go, right? You have to work with them as you go. You could use whatever is under your belt at this time.
So it's only for like the first one.
Okay, so look at the next one. It's an absolute value function that has vertex at negative 2. So if I were to graph it in its glory, right, the whole root x, absolute value of x minus 2, that bottom one, what would it have looked like? It would have looked like this, right? But we only have to graph it from 0 to 2. So it starts from negative 2 and it goes to 0. Why? Okay. And then what about that one? What value does it have at x equals 2? 4. That's too big. Okay. And then what else can we put here? 7. And it would be a 5. Good. Okay? Are we okay with this? Oh wait, should we have closed anything? No, we're good.
Is that a circle on x is equal to negative 2, or is that just 2 lines meeting?
Huh?
Is that a circle on x is equal to negative 2, or is there just 2 lines meeting?
X equals negative 2? Oh, it's just 2 lines meeting. I was just saying that there is a vertex there. Like that, okay? All right. Well, looks like I'm going to finish this lesson after all. Okay, absolute value. What does absolute value do? You can put absolute values in 2 different places. One is you can put absolute value around a function. So for example, look at this one. F of x is equal to, now this is a parabola. Who can give me an equation that would possibly define this parabola? There could be many answers. Yeah, Adam?
Top left.
Uh-huh. Top, yeah.
X squared plus 3.
Minus 3, right? Because it's moved down.
Yeah.
Now, suppose I took that one. So let's take a look at g of x. G of x, if I took that function and I put absolute values around it, that's what g of x would be. So basically, what absolute values do is take the part of the function that's negative and make it positive. So take a look here. All this is the part of the function that is negative. Okay? So below x-axis means it's negative.
There's no way. Yes,
It is. Okay. All right. So what it does is it takes that one and moves it up like this. Okay? So let's graph this now. All right. Okay, look, x squared minus 4x plus 3. Okay, you can put in the calculator, but who wants to do that? Okay. Let's factor. Do you guys remember how to put it in vertex form? Yeah. Complete the square, right? So, plus 4 minus 4. Okay? So this is going to be x minus 2 squared minus 1.
Why'd you do it? What? Can you do x minus 3, x minus 1?
Well, that wouldn't give it to you in vertex form. That would just factor this and you would find the zeros. But I want to put it in vertex form. So this tells me that there is a vertex at 2 and minus 1. Okay. So you split it here. Okay. X squared. Okay, so what you have to do is take this number divided by 2 squared, which gives you a 4. And that gives you a 4. Now, if you added a 4, you have to subtract a 4 from the same side in order to keep the equation balanced. Okay? We're going to go over this later, but
So you can just add in a 4, or like whatever number it would be.
whatever number it is, and then you have to subtract from here. How did you guys forget this from last time? Okay, so then you factor it x minus 2 squared minus 1. So the vertex is 2 and minus 1. Okay? Now, if we go over 1, we're going to go up 1. If we go over 2, we're going to go up 4. So this is what the parabola looks like. Okay? Now, that's f of x. Now I want to graph g of x, which is absolute value f of x. So for that, you take the negative part and you flip it. So it will look like this. Okay, so that red one is that. Yeah, I mean, for yourself anyway, somewhere. Now, I should have given you 2 grids for this. But basically, this hits 2. I'm going to do a very rudimentary one here, okay? Now, let's go back here. What if you have this, where it's absolute value of x? Absolute value of x, right? So basically, it's like this. If this is f of x equals x minus 2 squared, then g of x is x minus 2 squared. So do you see how like the x inside has an absolute value around it? Okay. What this does is this. It gets rid of everything with a negative x. and duplicates what's left over. So do you see this? Okay, that's this, and then it gets duplicated. Okay? So now, can we do that for this? We're going to get rid of anything that's negative. So this is the positive part. We're going to get rid of anything that's negative, like that. Okay? And then we're going to duplicate that. Like so. Okay?
We duplicate without the word vertical.
Mm-hmm.
With the y's in this case being well scale by 2.
Mm-hmm. All right? So, I hate to do this to you, but this is going to be due tomorrow. Okay? Better now than later. All right? I know Dodgers do have a game tonight. All right.